So previously we've discussed how Gibbs free energy depends on temperature. Let's now discuss how Gibbs free energy depends on pressure. As we do this, we're going to start dealing with what are called non-standard conditions. And so we're going to talk about how you can calculate delta G at non-standard conditions. And this will also connect to concepts that you've learned previously involving equilibrium. We're going to consider this equilibrium reaction between 2NO2 gas going to N2O4 at equilibrium. And we're told that delta G standard for this reaction is minus 6.0 kilojoules. So I want you to remember what that superscript 0 means, what it means to be at standard conditions. I'll remind you that standard conditions mean if you have a reaction occurring in the gas phase, all of the reactants and products are present at a pressure of 1 atm. So let's think about what would happen if you had 1 atm pressures of NO2 and N2O4. Which way would the reaction proceed under the standard conditions? The value of delta G standard is negative 6.0 kilojoules, and since it's negative, that tells you the reaction is spontaneous in the forward direction at standard conditions, meaning that at standard conditions, this reaction would proceed to the right. But what would happen if you did this reaction with pressures of NO2 and N2O4 that were not 1 atmosphere? Very often, we're going to be working with systems that are not at standard conditions, where we don't have 1 atm pressures of everything. And so we're not going to be interested in what the value of delta G standard is. What we're interested in knowing is the value of delta G under these non-standard conditions. So we would express that as delta G without the superscript 0, right? That's the non-standard delta G. Now we can relate the non-standard value of delta G to the standard value of delta G via this equation that connects the two states. Delta G at non-standard conditions is equal to the delta G at standard conditions plus RT times the natural log of capital Q. We've seen capital Q before, back in chapters 6 and 7 and 8, and I'll remind you the capital Q refers to the reaction quotient. Now, the reaction quotient takes a functional form that is very similar to the equilibrium constant expression, right? So if we were to write the reaction quotient expression for this reaction in terms of pressure, we would say that it was the pressure of N2O4 over the pressure of NO2 squared. Products over reactants raised to their stoichiometric coefficients. And the equilibrium constant expression would have the exact same functional form. The only difference between these two expressions is that you plug equilibrium pressures into the K or Kp expression. So you have to know that your system is at equilibrium in order to plug the values into K. If you're not sure whether your system is at equilibrium or not, or if you're in an initial state, then the values get plugged into the Q expression. That's the difference between the two. You also, earlier in Gen Chem, saw the relationship between K and Q. I'll remind you, you saw that when K was less than Q, then that means the reaction shifts to the left until you get to a situation where K and Q equal. If K is greater than Q, then that means the reaction shifts to the right. And if K is equal to Q, then that means your reaction is at equilibrium. Now, you've seen this before, and we talked a little bit about why this was the case. I talked earlier about how K represents what you want, and Q represents what you have, and so you can think about predicting the shift based off of that. But we're about to see how thermodynamics and energy connects to all of this. And additionally, when you look at these reaction shifts left, reaction shifts right, it starts to look a lot like the spontaneity conditions that we've been discussing here in this chapter. So let's summarize the spontaneity conditions that we've been discussing so far. There are 3 different spontaneity conditions that we've looked at here over the course of chapter 10. There's one that deals with delta S universe, there's one that deals with delta G of the system, and there's one that deals with the comparison between K and Q. And let's talk through what we've discussed with regard to all of these. So we said that for delta S universe, reaction is spontaneous or a reaction shifts to the right if delta S of the universe is positive. Reaction is non-spontaneous or it shifts to the left if delta S of the universe is negative. And the reaction is at equilibrium if delta S of the universe is equal to 0. Our spontaneity condition for delta G of the system says that reaction is spontaneous if delta G is negative. It's non-spontaneous if delta G is positive, and you're at equilibrium if delta G is equal to 0. And then for our K versus Q comparison, going back to chapter 6 when we talked about equilibrium, said that if K is greater than Q, the reaction shifts to the right, and if K is less than Q, the reaction shifts to the left, and if you're at equilibrium, then K is equal to Q. All of these concepts are all interconnected to one another. Whenever you have a situation where the delta S of the universe for a reaction is positive, then the delta G of the system for the reaction has to be negative. And you're also in a state where K is greater than Q. All of these things are connected to one another. All of these things have to simultaneously be true for a system that is spontaneous, or a reaction that shifts to the right. If you have a reaction that is shifting to the left, meaning that you're dealing with a reaction that is not spontaneous in the forward direction, then that means that the delta S for the universe would be negative for the forward direction of the reaction, right? Delta G of the system would be positive, and you'd have a situation where K is less than Q. All of these things are what's causing the reaction to shift to the left, right? The reverse of the reaction is occurring. It's not spontaneous in the forward direction. And if you're at equilibrium, then all three of these things have to simultaneously be true. The delta S of the universe must be equal to 0, the delta G of the system must be equal to 0, and K must be equal to Q, and that establishes your system at equilibrium. All of these things are all connected to one another, mathematically speaking. So the reason why a reaction shifts to the right when K is greater than Q is because as the reaction shifts to the right, you are minimizing Gibbs free energy and you are maximizing the entropy of the universe. That is what all systems want to go towards, right? You want to try to increase the entropy of the universe and you want to try to decrease the Gibbs free energy of the system. That is what this is all about, and that's how all these concepts are connected. That's how we're able to connect equilibrium to thermodynamics and energy. So let's take a look at a practice problem involving this reaction between NO2 and N2O4. We're told that initially the partial pressure of NO2 is 0.01 atmospheres and the partial pressure of N2O4 is 200 atmospheres. So we're not at standard conditions here. We're given the standard value of delta G to be negative 6 kilojoules, and we have to calculate the non-standard value of delta G at 298 K with the pressures that have been indicated here. So to do that, we use our equation. Delta G non-standard is equal to the delta G standard plus RT ln of Q. And we can go ahead and calculate the value of Q for this reaction. And the Q that we're dealing with here is going to be Q sub P in this equation. So we can calculate the Q sub P with the initial pressures that we were given, right? That's our pressure of the N2O4 over the pressure of the NO2 squared. And that's going to be 200 over, for the NO2, we have 0.01 atmospheres squared. The value of Q for the reaction under these conditions is 2 times 10 to the 6th. So let's plug that in. Delta G under these non-standard conditions is equal to the standard value of delta G, which is negative 6.0 kilojoules, plus R, that's going to be the 8.314, because you want to make sure that you have joules in your answer. And R has joules, delta G standard has kilojoules, so we have to make the energy units compatible. I'm going to turn the joules into kilojoules right now. So divide by 1,000. T, we're told, is 298 Kelvin, natural log of the reaction quotient, so that's natural log of 2 times 10 to the 6th. Now, in terms of the units, there are a couple things that are worth mentioning here. First and foremost, we converted the joules into kilojoules, so that's good. And Kelvin cancels out Kelvin. And when you look at this, it now appears as if you have units of kilojoules for the delta G standard term and units of kilojoules per mole for the RT ln of Q term. And so you might think that there's an incompatibility in the units. But I will remind you, something that we talked about in the thermochemistry chapter, back in chapter 9, is when you have a chemical reaction and you write a delta H next to the reaction, it's in units of kilojoules, but we imply that it's kilojoules per mole of reactions. The same thing holds true when we're talking about delta Gs for reactions. So if you have the delta G given for a reaction, we write that it's negative 6.0 kilojoules, but it's implied that it's 6.0 kilojoules per mole. So we can write that in. This part is implied. And we can go ahead and now write that in down here, 6.0 kilojoules per mole. And so what we end up with is all of the units being compatible here between these two terms. Therefore, we can plug the values into our calculator now and find what the non-standard value of delta G is. And when you do that, you end up getting 30 kilojoules per mole of reactions, or that is just written as 30 kilojoules, because again, the per mole of reactions is implied. All right, we found what the value of delta G is under these non-standard conditions. And now we have to ask ourselves whether or not this reaction is still spontaneous under the non-standard conditions. Remember, the reaction is spontaneous if you're at standard conditions. But what about under these conditions? Since the value of delta G is positive, we would say the reaction is not spontaneous under these conditions. So no, because delta G is greater than 0. And since the value of delta G is positive, the reaction will shift to the left. The reaction is not spontaneous in the forward direction, and so it will go to the left instead. It goes in the reverse direction. Next up, we'll go into some more depth with these calculations and discuss a little bit more about finding the value of K for a reaction.